So now that we've seen how to add constraints, let's actually look at a couple examples. First one we're going to look at is basically just a nice easy one, so to get used to how to actually write constraint equations, and then the second one will be one doing an integral one. But the first one we're going to look at is, let's say we have a object here rolling down without slipping along an inclined plane here, and we want to use our coordinates y and theta here. Okay? So we want to be able to write the constraint and then basically just look at the partial derivatives of these just to write that down, just kind of see what they are. So first things first, again, as we know our constraint here, which is going to depend on g and theta, must be equal to 0. Okay? Now the constraint in this case is that since it's rolling without slipping, what that means is that these two things are not independent from each other. Right? If it was rolling with slipping, what would be happening is that this thing would just be rotating, which means it would have an angular velocity determined by theta, and then y would, basically represent the distance that this thing would travel, right? Because y would also be the distance along the plane here. So basically meaning that y then would be independent of theta, since theta would just be how this thing is actually rotating, right? The angular velocity, and then y would represent how far it actually moved along the plane. But since it's rolling without slipping, then what you know is that this arc length y here is the same thing as the distance at which this thing travels along the plane, meaning that as this thing rotates, it has undergone the amount of distance of the arc length, which is the same amount of distance it's gone down the plane. And we know that arc length then is equal to the radius times y, right? So again, basically meaning as long as this thing is rolling without slipping, we know then, let me iterate this a little bit better. Let me call this s here. So we know that y must be equal to s, which is then equal to theta times r, right? So here our constraint equation is simply that y minus r times theta must be equal to 0, right? So this is our constraint equation. So in this case, g y of theta, same notation as before, that is equal to y minus r theta. So this is actually our constraint equation. So from here we can see that the partial derivative of g with respect to y must simply be equal to 1. Simultaneously, the partial of g with respect to theta is equal to simply r. Okay. So this is our first, again, example. So again, just kind of seeing how do we actually write the constraint equation and then be able to take its partial derivatives. So next one we want to look at is one using the integrals. So here what we want is we want to look at, so let's say x-axis, y-axis. We want to look at a curve y of x, which then connects 2 points, where the first point is going to be at minus a, second point then is going to be at a. So we want to see what path will connect these two. So this is my y of x, which is bounded by the length of the string. So the string must have length of L to it. Good. And we want to find this so it has the largest amount of area. So basically we want here that the area, which is generated inside of here, so A is a maximum. Maximum. So again, we want to extremize the area, but we want to have a fixed length at which this can undergo. Which means that we have a integral constraint as well as our functional. So here our functional is simply going to be equal to the area, which means we want to integrate over the differential area, right? So basically here we're looking for what type of shape are we going to get that's going to extremize the area. Basically meaning, are we going to have something like, I don't know, maybe a rectangle, which has a perimeter. In this case, the perimeter is equal to L. We're going to get something like a triangle, say something like this, where again the perimeter of the triangle is equal to L, or we're going to have something like a circle, where the circumference of that circle is equal to L. So this is what we're looking for. So we're looking for what, if I have this finite shape of L, or finite length of L, which one of these is going to maximize the given amount of area. Right? So let's pick our original curve. Let's pick any point on here. So let's say this is the point that we're interested in. So we're going to cut a small section here, so that this point then has a height of y. So if this is the x direction, this is the y direction. So the differential area then here, dA. So our differential area here will be, again, y times the thickness of this, which along this particular axis is simply dx. So this is going to be y times dx. So here, we're going to get then that the differential area is simply going to be the integral from minus a to a of y dx. But since we have a constraint, our constraint expression then is going to be k, which is going to be equal to what? The integral over the differential length of this thing, which we're going to call ds, has to be equal to simply L. Right? Now ds, same thing as before, we know is just going to be equal to, let's factor out the dk, so it's going to be the integral then of what? The square root of 1 plus y prime squared dx, and this has to be equal to L. So good. So looking at both of these, so from here we can see that f then is simply equal to y, and then from this one, this is then going to be g. So g then is equal to the square root of 1 plus y prime squared. So, good. So now we can plug this into our expression that we just came up with, which said that the partial of f with respect to y minus then d dx of then partial of f with respect to y prime plus lambda times partial of d with respect to y minus then d dx partial of g with respect to y prime. All of this must be equal to 0. Right? So good. So from here, partial of f with respect to y is simply equal to 1. There is no y prime component here, so this is going to be simply minus 0. And then I get a plus lambda times partial derivative of g with respect to y. Well, there is no y dependent, so that guy is just simply going to be equal to 0. Minus then d dx of, so this is now going to be equal to y prime divided by the square root of 1 plus y prime squared. And all this then has to be equal to, again, 0. So good. So let's separate this. So let's get rid of all this stuff. So let's separate and rewrite. So this is going to become equal to, so this has a negative sign overall. I'm going to bring that to that side, divide by 1 over lambda. So I get 1 over lambda then is equal to d dx of then y prime divided by the square root of 1 plus y prime squared. From here, we can then separate and integrate. So from here, we're going to get what? The left-hand side is going to become simply x divided by lambda plus some sort of constant. So in this case, I'm going to subtract off c1. And then the right-hand side is going to become the integral of simply this, which is just that. So it's going to become y prime divided by 1 plus y prime squared. So that's this guy. Good. Good. I can redefine that variable, so actually let me put the lambda down here too, just to make it a little bit nicer. So ultimately this is going to become x minus c1 then is equal to lambda times y divided by the square root of 1 plus y prime squared. Good. From this guy, we then, oops, that's a y prime. So from here, we now want to solve for y prime, and then we're going to separate. So from here, we get a, what, y prime, which is equal to dy. Dx is then equal to x minus c1 times, or sorry, divided by the square root of lambda squared minus x minus c1 quantity squared. So from here,